Hello everyone. Today we'll be talking about time-space trade-offs in computer science. So that's a very important topic. Many of the algorithms in computer science make use of this time-memory trade-off. It means if you would like to compute something fast, then is there a way to speed up the processing by using more space? And since having speed operations is one of our main target in computing jobs, so time-space trade-off is almost inevitable in every place. Okay, we usually have this perspective from the time opinion. So we would like to have something fast, but the other way it also works. Okay, so sometimes you are in a space limited environment and you would like to use less memory. Then you can ask the same question in the other way. Can I make more processing to have less space? This is rare, but it may happen. So going back to the original discussion, so what I would like to do is I would like to speed up the computation by using more space. So that means whenever I get the input, what I will do is I will have a prep processing on this input. I will compute something, store it, and then later when I need that, I will go and use it. I think remembering the functions in programming languages will help that. Okay, so what I have in my program, okay, so I have a function, right? A function f, okay? And this function f has some input. And what happens is it computes something and then returns a value. Okay, so let me say the return type, whatever. Okay, so this is the general execution, right? Now the question is, once you have this function, would it be possible for you to visit all possible inputs to that function? If that is feasible, then that means if I run this function on all possible inputs, then I will have a list, right? And on this list, I will have the return values corresponding to input values. We call this a lookup table. That means once I have this table, I do not need to have this function in my program anymore. I don't need to execute it. Why? Because I need all possible combinations in this lookup table, and whenever in my program at some other position I need the value to be returned from that function, I will not execute it. I will go to the corresponding row in the lookup table and just fetch the results. Fetching something from a lookup table is surely a lot speedy than executing a function. So that is why that speeds up our computation. But on the other hand, you see, now I need to reserve space for this lookup table. And that is why I am trading more space to gain in time. Okay, so that's called the time memory trade-off. Actually, there is a nice example for this approach, an analogy. So in the 17th, 19th, even the early 20th century, so there were some thick books in the libraries that include some tables. For instance, the logarithm table. Okay, so since compute are not much known and they are not exist something and need the logarithm of go to that book and find that number and read the corresponding logarithm value for that purpose. But that is a good analogy to understand what time memory trade-off looks like in terms of lookup tables. Okay, so one more thing maybe I need to mention here, to prepare these lookup tables, to prepare the input, so that is the pre-processing time. And that pre-processing is achieved only once, okay? And then we use it many times later. So that is why, although it is better to have a pre-processing, efficient pre-processing time, so even if it is something heavy, if you will do it once and then you will use it forever, then it worth the effort. Okay, so let's start visiting some examples. Okay, so n log n is the best complexity for sorting, okay? But actually, it is possible to build O(n) time sorting algorithms, and we will see one of soon, okay? That the best time complexity can be n log n, then how can I have something with a linear time? So there happened an internet interruption, so I'm going back. Okay. So we were talking about this sorting by counting. Okay, so the question was, okay, so what determines the rank of an item on a given list? When I have such an input sequence unsorted, I would like to find the position of that element in the sorted sequence. Where is it? Okay, so I will call this the rank of this item in the sorted sequence. Actually, the rank of an item in a given list is determined by the number of items that are less than it. That means if I would like to find the rank of AI, okay, what I need is I will just compare this AI with all the remaining guys and we'll count the ones that are less than AI. And then that means the position of AI on the sorted list is the number of items that are less than it plus one. Okay. So for instance, let's first focus on the sequence. Okay, so this is the sequence we are given. Okay, so if I would like to find the position, the rank of, let's say, 84, okay, what I need is I will go and check all the previous items. So 62 is less than 84, so this will appear before 84 on the sorted sequence. 31, yes, right? And 96, no, it is not. Okay, so 19, yes, and 47, yes. So that means there are 4 integers that are less than 84 in the given sequence. So that is why 84 will appear at the 5th position. Okay, So once I have this observation, then I would like to come up with a good algorithm to have those counts. The first an additional array. So that's the count array. And on this count array, what will happen is at the end, at each position, we will see the number of integers that are less than that position on the input array. Okay. And how it goes. So here is the algorithm, pseudocode of the algorithm for making this. So initially, you initialize everything, and then we start. We start with the first position. Okay. So 62. And I check the next position. So 31. Okay. Is 62 less than 31? No, right? But 31 is less than 62, right? So that means for the count of 62, so the number of for the number of integers that are less than 62, when I see 31, I should increase it by 1. Okay, so I make this position by 1. So initially it was 0, now it is 1. And then I compare 62 with 84. Right? Is 84 less than 62? No. But that means if this is the case, 84 is greater than 62, so I will increase its corresponding count. So that means at the end of each comparison, you either increase the first one or the second one. Okay, so 62 and 96. Okay, so 96 is not less than 62, so we have the increase here. So 19, yes, 19 is less than 62, so that becomes 2. And 47, yes, 47 is less than 62, so that becomes 3. So at the end of the first stage, I am here. I have detected that there are 3 numbers that are less than 62, and I am done with 62. For the others, during my traversal on the array, or during my initial pass on the array, I have already noticed that. So there is one item that is less than 84, and there is one item less than 96. And I know it is the one that I have investigated. But I will continue now. I will continue with the next one. So that is why we have these 2 for loops inside. Okay, so now 31. I will also do this. Okay, so for 31, is 31, I'm trying to find the number of items that are less than 31. Is 31 less than 84? No, then that means I should increase the count of 84 to 2. Okay, so 96, is it less than 31? No, so that means I need to increase it again. So 19 is less than 31, yes, so I make it 1 now. Okay, and 47 is greater than 31, so that is why I introduce a 1 here. Okay, at the end of the second stage, what happens is now I have these numbers. And you continue with the 84 and then 96 and then 19, and once you reach there, actually you are all done. Okay, so at the end you have those counts. Once I have these counts, I know the positions. Okay, so what will happen? I know that 62 should go to the third position, fourth position. Why? Because there are 3 items less than 62. So you move 62 here. Okay. So for 31, I know there's only one item less than 31. So 31 should be in position 1. So let's make it 0, 1, 2, 3, 4, and 5. Okay. 84 has 4 items less than it. So these are 0, 1, 2, and 3. So that is why 84 should appear at that position. Similarly, for 96 and then the 19, so that's the smallest one, and then I have the 47. You see, okay. I did everything very nice. I have the sorted sequence, and what is my complexity? When we study our complexity, we see that it is O(n) square again, right? So because of these two for loops, okay. And once you see that this is an O(n) square algorithm, you start thinking about it. You say that, okay, for this one, I'm using extra space and I'm having a O(n) square complexity. Does it worth the effort? Okay. And you remember that we have the selection sort, we have the bubble sort. These are all O(n) square algorithms, right? So insertion sort. So these are all O(n) square algorithms. And what happens is we do not need an extra space for them. I'm using an extra space and I'm not gaining anything in terms of the time complexity. That means this effort does not worth it, right? But there is one thing good about this algorithm. So with all the others, you swap the elements during the process. But with this algorithm, you move the elements only at the very end. Okay, so there is no element movement. So that is something good because moving those elements sometimes might be time consuming. And a very good example of this one maybe is, okay, so let's assume you have some statues in a museum. So these are ancient, very valuable, priceless statues, and you would like to sort them according to their heights, okay? So that means you will need to move them. But since they are very precious, so you don't want to move them too much, okay? So maybe using a sorting by counting will make this job more appropriate because you will have only one movement, okay? So some sort of analogy, I don't know, okay? So the only advantage of this algorithm when compared to selection sort and bubble sort is that it doesn't swap the elements more than once. But with the selection sort and bubble sort, we have the selection, we have this swapping movement very frequent. However, we have another approach, again with the same thought, but it will provide us a linear time sorting algorithm. Okay, but to have this linear time algorithm, I need some extra information. And what is this information? Whenever I'm given the sequence, I would like to know the lowest position, the lowest value, the minimum value, and then the maximum value. For instance, if I'm given 13, 11, 12, 13, 12, and 12, so I will say that so the minimum one here is 11, and the maximum one is 30. Good? Okay. Now, I know that all the elements in this array are in between these guys. Then what I can do is I can create a list. I will create this list and I will reserve a spot for all the elements from the lower bound to the upper bound. In my case, I have 11, I have 12, and I have 30, right? And since I have those only 3 different elements, so the length of this sequence is equal to U minus L, right? U minus L plus 1, sorry, okay. So 13 minus 11 plus 1 is equal to 3, and I have 3 elements here. And the smallest one will appear at position 0, the next one at position 1, and the next one at position 2. Okay. To find the position of any element I in between L and U, what I should do is I should go to the cell with the index I minus L, right? So this is my input sequence, and this is the array that I will store some values. We will come to that later. Okay, just I would like to make clear that how you will know that 12 is mapped to position 1, because for 12, so L is 11, 12 minus 11, it is equal to 1. So you go to the position 1 in a zero-based indexing. If it is 1-based, so you should add 1 to that. Okay, so these are the just easy warm-ups. And then what is the idea? The idea is whenever you provide me the sequence, I will pass over this array and count the frequencies. And I will store them in the array that I mentioned. Okay, so this is the distribution array, let's say. Okay. So in the first step of the algorithm, you first initialize the frequencies, and then you just visit every position and get the corresponding frequencies. 11, that appears 1 time, 12, that appears 3 times, and 13, that appears 2 times. Good? Okay. And we maintain in the array the cumulative frequencies. With the cumulative frequencies, I mean, actually, so this is 1 and this is 4 because 1 plus 3 is equal to 4, okay? And this is 6 because 2 plus 4 is equal to 6, okay? So with this way, so let's think about it, okay? I have 1, 2, 3, 4, 5, 6 elements, right? So 1, 2, 3, 4, 5, and 6 elements. Okay, and the 6 elements, one of them is 11, right? And 3 of them will be 12, and 2 of them will be 30. Okay. So in other way, if I just visit the elements one by one, whenever I hit a value 13, I know that this 13 should be in this range, right? And then this one will be in this range, and this one will be in this range. So notice that there are 1 element here, there are 4 elements here, and there are 6 elements here. In other words, those cumulative counts just give me the position of the last index that the corresponding item should be placed in. If it is a 1-based indexing. If it is 0-based indexing, I will just decrease it by 1. We will see this now for sure. Okay, so this is the main algorithm. Now, what I will do, I have the counts, I have the cumulative counts, and I have this distribution array. I will start, and then I will check the first item. So that is equal to 13. In my distribution array, which item, which position is devoted to 13? So I know that L is equal to 11, right? And my current value is 13. 13 minus 11, that is equal to 2, right? So this is a 0-based indexing, and I will go to the last position on the D array. It tells me that, okay, so for 13, you should go to position 6 and put it there. Okay, since this is a 0-based indexing, so what I will do is I will go to position not to 6, 6 minus 1 is equal to 5, okay? And on this position, I can just put the element 13, okay? And the next one is 11. So for 11, oh, by the way, whenever you insert 13, you should decrease this value by 1, because next time, whenever you hit the 13, you will need to put it not to the 6th position, but just the position in front of it. Okay, so this way you go on. But this algorithm, it's more convenient to do it from right to left instead of my previous attempt from left to right. So let's follow the convention used in the algorithm and do it from right to left. That means I should start with the 12, the fifth element. Okay, so 12. So 12 minus 11, it's equal to 1. I go to position 1 and I see that it's position 4. Okay, position 4 means 0, 1, 2, and 3. Go and write it to there. And once you write it, you decrease this value by 1. Now it is 3. Okay, so the next one is again a 12. Okay, so I go to the, again, 12 minus 11 is equal to 1. I go to the corresponding position and I see that now it writes 3. 3 means I should write this new element to position 3 minus 1 is equal to 2. So I write it here, okay? And then the next one is 13. 13 minus 11 is equal to 2. Go to position 2. So that is 6. 6 minus 1 is equal to 5. And write the 13 there. Okay, you are done. Oh, I again hit a 12. I go and 11 minus 11 is equal to 0, so I will go there. Okay, I will go here, sorry, and then once I go to that position, it tells me 1 minus 1 is equal to 0, so I write 11 there, and the last one is 13. I go to the corresponding position, and that corresponding position is equal to 5. And 5 minus 1 is equal to 4. I write 13 here. Okay, so at the end I have 11, 12, 12, 12, 13, and 13. Okay, so with this distribution sort, now it makes sense. Why? Because I have only one for loop here, and these are all linear operations. So that means the overall complexity of this one is now linear. That is very nice, but it comes with a cost, right? So once you have these numbers, you will need to maintain a D array. And what is the size of this D array? D array is the size of this D array is the maximum of the given list minus minimum of the given list plus 1. Okay. And I say that, okay, so this distance should be a reasonable one. And I will give you an example and you will immediately get it. Okay, so let's assume I give you this sequence. Now here I write something 4 billion. Okay, now what happens? You have the maximum 4 billion and you have the minimum 13. Okay, although you have only very few elements, your algorithm will go and create a distribution array for how many elements? 4 billion minus 13 elements. Okay, and that's a huge array, and it might not make much sense. Okay, so that is why the success with this distribution counting comes with reasonable, feasible, lower and upper bounds, and it depends on that depends on the input. What does it mean? It means that for the distribution counting sort, you pray that the input would be something reasonable, and that moves it away from a general sorting algorithm. For the insertion sort, for the selection sort, bucket sort, you do not care what is in the input, right? So you just do it. But with the distribution counting sorting, so you have to take care of this fact. But indeed, if you know your input is suitable in that sense, so that makes that's a very nice sorting algorithm. Okay, moral of the story: to speed up the sorting process, what I do is I use some extra space, and in this extra space, by the end of a pre-processing attempt, I store some values, and I use these values in my sorting stage. So that makes me, that gives me an efficient sorting algorithm. I wanted to repeat it because two things are important. So I'm using extra space, so that makes it a time memory trade-off, okay? And I have a pre-processing stage to fill the values in that additional space. Okay. After this warm-up, we continue with the main meat of this lecture. So it is the hash algorithms and hashing. Okay, so what is hashing? Since time memory trade-off is a very powerful tool, let's think on it from a different perspective. You know, search and retrieval are fundamental operations in computing. Whenever I have an array, I would like to have efficient search and retrieval operations. Okay, so we know that to make this fast, what I can do is I can just sort the list, okay? And that comes with an n log n complexity. However, if I sort the list and keep it in sorted order, then I can run a binary search and provide the search in logarithmic time. So that is good, but it requires n log n processing, so might be heavy. We don't know. Okay. What are other alternatives? When you give me an array, I can also create a balanced binary search tree, right? Still, I will preserve my log n complexity, right? But what I will need is, I will need to create this binary search tree. And in addition, during the insertions and deletions, I need to take care of it. So hashing in that scenario provides us something in the middle, okay? So with the hashing, actually, what we mean, let me try to sketch it here. So I have an input array. What I will do is I will create slightly larger additional array. And what I will do, I will reorganize the items. I will move these guys to this table. We call this the hash table. Okay, so we move this guy to here. We move this guy to here. I don't know, we move this to here. And surely moving the items to their appropriate positions should be done in a deterministic way. That means I have a function that maps this value to this address. Okay, so I have a function, and I feed this function with a value, and it provides me an address. Okay, and I go to that address and I just copy this value. So this is the main idea behind hashing. Okay, that means next time, if you are curious whether this particular value exists in your input, then you can do it very fast, right? So the only thing you need to do is you will run this function. Okay, so you will compute this function, we call this the hash function, on your value. So this will provide you an address, and if this value exists in your input, it should appear at that address on the hash table. Okay, this means search is very easy. Okay, so if I would like to search for X, I will go and compute its hash. We call this the hash function, hx, okay? And this will give me an address Y. I will go to the hash table and check position Y to see if it is there or not. Okay, so this is the main idea. Okay, so what is important here? Again, let's remember that we are studying this topic in time memory trade-off. Okay, so that means I'm using more space. Usually, this size of a hash table is average 2 times of the input size. Okay, so this is my input of size n. Usually, I will be maintaining a hash size. Okay, is an increase. And maintain it by this hash function, hash table, or this. Sorry, guys, again, there appears something on the Zoom servers. I don't know. So let's go to that hashing and continue our discussions from there. Okay. What we were talking about, so we said that the size of this hash table, should not be larger than the input. If this is my input and I would like to create a hash table, so the size should not be very large. In addition, the hash function that is hx, right? So I feed the value of an item to this hash function and it returns me a value. This function should be something very simple, should be fast. And I guess you already noticed that this is a good idea, but what will happen if 2 of the values just hit to the same address? This is inevitable if those 2 items are same. It's possible that in the input I have some repetitive items, or even more, it is possible that the hash of A might be equal to a hash of B. So that means they will be hitting to the same position, and this will create a problem. We will see that actually those collisions are unavoidable, but we do our best to have this hash function distribute the objects as evenly as possible in the new space. Okay, so these are the 3 properties we look for in a good hashing scheme. Okay, and we will visit this again later, but the main advantage is the average time of search becomes constant with the hashing. Okay, so how do we do hashing? There is an initial step, usually not much discussed in detail, but that might turn out to be a real headache in practice. Okay, so hash is a function, right? So hash is a function, and that requires this input to be a number, okay? So to be an integer, okay? And what if I would like to compute the hash of a string? Okay, so this is a string, and I would like to compute the hash of this string. So this is not a number, and it's a mathematical function, so that expects a number. So that means I need to convert this alphanumeric sequence into an integer into a value, okay? This conversion, sometimes called computing the hash code of this object, can be done in various ways, okay? So we all know that actually whatever the input is, in computer, it is just zeros and ones, right? For instance, string. So string is 1 byte for S. We don't know 0, 1, 0, 1, 1, 0, 1, whatever. And 1 byte for T, 1 byte for R. It goes on. So that is a binary sequence. And on this binary sequence, I can do anything to map it to an integer. But this initial mapping is not the hashing itself. We are just trying to find the representation of the object. Usually, you might have heard about those cyclic redundancy codes, okay, cyclic redundancy codes. And those codes compute an integer given anything, okay? Let me give you an example. You go and download a file from the internet, okay? So let's say this is a huge file, okay? So 1 terabyte file. And once you download it, you would like to make sure whether you have downloaded the correct file or not. How you can do this? One way is to download it again and compare it with the previous one. So that will be very costly, right? So that is why actually what we do with those cyclic redundancy codes, while downloading the file from each symbol by following a simple computation algorithm, you come up with a number, okay? And this is, let me say, 256-bit number. And then you say that if you have downloaded the file correctly, if you compute the CRC check on your file, you will again see the same number, okay? And this is a way of producing codes. What else? So maybe a very simple one. So for instance, for string, what I can do is I can say, okay, so what is the value? What is the byte for G? So you have this byte, and that is actually a number, right? In an ASCII code, right? So in binary, so that's an 8-bit binary number, and you get its number, and you add it with the N, you add it with the I, so you add these things up, and you come up with a number, and you say that, okay, for the string, I will use this hash code. You know, this is dangerous because what will happen, the hash code of string will be equal to hash code of SRTNIG, right? Because they have the same symbols, same characters. So summing these up will give you the same thing. So that is why using those cyclic codes might be useful, but here our aim is not to visit how to create an efficient hash code, but let's assume you have this hash code, and if it is an integer, you already have it. And in the second step, you apply the hash function, to the hash code of the object and get an address. And what is this hash function? Hash function is usually something like that, okay? So it is the X input mod M. What is this M? M defines the size of my hash table. Because what is X mod M? It is something between 0 and M minus 1. So that means this hash function will return me something from 0 to M minus 1. So this M is the size of my hash table. Whenever I see it, I will just go and put my value there. Okay, so this is the hash scheme. Okay, now the main difficulty. Whenever you compute the hash values of items in a given input, collisions are unavoidable. for two reasons. One, there might be copies of the same item in the input sequence. They will go and hit the same address, same hash value, same hash function, right? And two different values might somehow get the same hash result. And that is why those collisions are unavoidable. Okay, so once I have these collisions, what I will do? Okay, so there are two ways to deal with this collisions. The first one is called the separate chaining. And first, let's focus on this one. Separate chaining means this is also called the open hashing, okay? Actually, the size of my hash table is infinite. How can this be? This happens with an assumption. So we say that I will not keep the values in the hash table, okay? What I will do is I will compute the address of every object in the hash table, and that address in the hash table includes a pointer to a list, okay? And whenever I go there, I go to that address, I will not copy the value to that position. I will copy the value to the list that is pointed from this address. Let's have this on an example. So let's assume we have these objects, okay? A fool and his money are soon parted, okay? And this is my hash table. My hash table size is 13, right? And let's assume I have the hash codes for each of these ones, and then I have computed the hash values. What I mean is hash of A is equal to 1, okay? Hash of fool is equal to 9, okay? And hash of AND is equal to 6, whatever. And now I will try to do it, okay? So since the hash of A is equal to 1, I will go to my hash table. I will go to position 1. And at this position 1, I have a pointer. And this list is currently empty. So what I do is I just put A to here. And then for the second one, I go to the 9th position and I just append full to this list at the 9th position. You keep doing this for AND, okay, that's in the 6th position, his, so that's in the 10th position, money, it's in the 7th position, R, that's in the 11th position, and now we hit a collision. So the hash code of soon is equal to hash code of R, okay? That means these will have the same value and they are equal to 11, okay? When I go to 11, I see that it is already containing a list, but this collision is not problematic. The only thing is I will just copy this soon to the end of this list. Now the list on this array position 11 has 2 elements. And for the last one, so there is no problem. So you just copy the parted to its corresponding position. So what is good here is you don't need to worry about the collisions, because whenever a collision happens, nothing is problematic on your hash table. You just append the values to the list. But what is worrisome is some of those lists may become very lengthy, and that will affect my performance, right? Why I'm doing this? I'm doing this to have a better search complexity. So if this is my hash table. I'm looking for something, so something X. I go to HX on this table, so HX, so let's say it points to here. So there's a list, and if this list is very long, now I will need to check everything one by one, and I'm actually sacrificing my constant time search capability here, okay? So that is the disadvantage of the separate chaining, or it's also called the open hashing, okay? But no problem. So this is a way you can make things work. The second option to handle the collisions is called the open addressing. In this case, I have a closed hash table. Closed hash table means the values are stored in this hash table, okay? And it is fixed. This hash table size is fixed. It cannot be enlarged without rehashing, okay? So let's see what is open addressing, okay? When there appears a collision, I will need to check other positions, right? So let's assume I hit to here, and there is something already occupying that position. What I will need to do is I will need to go and check another position. But how I will find this address? In general, we can formalize it this way, okay? So key is the object hash code, okay? And then you compute the hash of this object, and you add an offset, okay? So initially, you compute, you check this position, HK plus F0. If it is occupied, then you check HK plus F1. If it is occupied, HK plus F2, okay? Very simple way for this F function is to assume Fi is equal to I. So that means if initially I will go to position HK plus 0 because Fi is equal to I will go to the original position. If it is occupied, I will check the next position. If it is occupied, I will check the next position. This is called linear problem. I'm linearly checking the positions. What else? So there are too many alternatives, but the most widely known and used one. So there is the quadratic problem. Same story, but instead of checking just the next cell, I will have some longer steps with the I square, okay? So initially, I will go and check HK, and then if this is occupied, I will check HK plus 1. If it is occupied, I will check plus 9, and then plus 4, and then plus 9, right? And then plus 25. You see, you are checking more distant positions. And what else you can do is, again, you can use a double hashing scheme. So my initial position will be HK plus I times a second hash function, okay? Since this key is the same, okay, so I should use another hash function, that's hash prime. So when I is equal to 0, initially, I don't need to compute it. But if it hits to something, then next time what will happen, I will compute this position, right? And the next time, if it is already occupied, 2 times whatever this value is, and then 3 times that goes on, okay? So let's have a hands-on example of how we handle the collision with the linear probing. The others are quite similar. That is why I will only do it with the linear probing. Assume that this is my hash function. Since this is my hash function, it is mod 11, okay? So that means my hash size, hash table size is equal to 11. So this is my hash table. Now, I will insert the elements into this hash table. The first one is 24. 24 in mod 11, so that's equal to 2, right? So I will go and write 24 here. 15 mod 11. 15 mod 11 is equal to 4. I will write it there, okay. 5 in mod 11. So it is 5. I go to the 5th position. Since these are available, vacant, I can just copy them. And then I have 37. 37 in mod 11. 37 mod 11. So that's equal to 4, right? So 4. I go to position 4 and it's alarming because it is occupied. Then I will check position 5. It is already occupied. Then I will check the next position 6. It is available. That is why you write 37 here. You see, although the original position for 37 should be position 4, it is now living at position 6. Anyway, you continue and you say that 27. 27 mod 11, so that's equal to 5. 5 is occupied. Check the next position. 6. 6 is occupied. 7. 7 is not occupied. I can write it here. Okay. 10. 10 is easy. There is no one here. I write it there. And what else? I have 26. And when it is 26, 26 in mod 11, that is equal to 4. It is occupied. You check the next position, occupied. Next position, occupied. Next position, occupied. And you need to write 26 here. Now you are done. Okay. This is the way how it works with the linear probing. Then these are the insertions, right? And I will do deletion later. Okay. How about if you would like to search for something? Assume I would like to search whether 27 is in this table or not. If 27 is in this table, it should be at position what? 27 mod 11. So that's equal to 4, right? I will immediately land into position 4. So 27 mod 11. So that's 5, right? So that's 5. I will immediately go to position 5 and check whether 27 is there or not. So that point is very important, okay? I go to position 5 and I see that there is an element which is not equal to what I am looking for. Since they are different, can I say that 27 is not in this hash table? You cannot say this. Why? Because maybe when 27 was inserted into the hash table, position 5 was already occupied. So that is why maybe you needed to locate 27, not to position 5, but to position 6, because you know that you are using the linear probing to handle the collisions. Oh, then you say, let me go and check the next position. And you go there and you see there is 37. Can you stop? No, you cannot, because maybe I need to, maybe at the time of the insertion, position 6 was already occupied, so we check position 7. So you keep checking next positions until you hit the value or you hit something that is not there. Okay, you hit something, you hit a vacant position. So let's make an unsuccessful search now. So let's say I'm looking for 6. Okay, 6, just 6. 6 mod 11 is equal to 6. So I go to the position. So let me clear this first. Oh, sorry. Okay, so let me go to the position 6. At position 6, I see that it is 37. It's not equal to 6. Should I stop? No, because the next cell is occupied. I go to next cell, it is 27, it's not 6. I check the next cell, it is 26, it's not equal to 6. And then when I hit the next cell, I see that it is vacant. Since it is vacant, now I can say that, so 6 is not in this list. Because if it was, it should be on the chain here, according to linear probing. If we understand this searching mechanism, then we also understood why deletion is very dangerous, okay? And it is difficult. So let me go to this one. So I will need to do some clearing on my, this way. Okay, I'm trying to clear these things so that we will be able to work on it better. Just give me some time to do it. Okay. Okay, now it is fine. Okay, so now let's study this deletion. Okay, so let's assume I would like to delete something. Okay, so let's say I would like to delete 27. Okay, I would like to delete 27. So I go to my hash table, I find its position, and what can happen is I can just immediately delete this guy. Okay, but if I delete this guy, there will be a problem. Actually, there can be a problem, right? So what I know is, let's assume, let's see the problem. Now, you deleted this one, okay, you deleted this one. So this is a vacant position now, and you are looking for 26. For 26, you know that 26 mod 11, it's equal to 4, right? 4. And then you go to position 4, it is occupied, and you check the next position, you check the next position. You will keep this check until you hit a vacant position. And then since you deleted 27 in the previous step, you will hit to here, okay? And this is deleted, this is vacant, and you will say that 26 is not in the hash table. Indeed, it is, okay? That causes a problem. So that is why on the hash tables, we do not delete the elements immediately, okay? So we just mark their positions as dirty. So let's assume I have 11 bits, okay? And those 11 bits just mark whether the corresponding position is valid or not, okay? So we call this the dirty bits. So whenever you would like to delete the 27, a good way might be to mark this position as dirty, but you do not delete the actual value. Now, if you do it this way, then the previous problem will not happen because you will be able to hit the cells and you will be able to find the 26. So this is a point that we should be careful while dealing with the hash functions. Okay, good. And what is the key performance metric on those hash tables? Okay, because you will be picking a hash function, you will decide on the hash table size, and you need to decide on a collision handling scheme, right? So these are the things you should do. So let's assume you decide you work on the linear probing, and what would be the key performance metric? So it is the number of accesses in successful or unsuccessful search. I'm looking for something. Did I reach this item in one excess, in excess to one cell, in excess to 2 cells, 3 cells, 4 cells, because I'm looking for something to be very fast. Okay, so 1 is the ideal if it is in the list. But due to those collisions, I may need to check more than one position, you know, from the previous example. So this is the cost for a successful search. Similarly, if the item is not in the list, is not in the hash table, it's an unsuccessful search, I should have something reasonable, right? While discussing these things, first we need to talk a little bit about the load factor. So what is a load factor? Load factor of a hash table is the ratio between the number of items in the hash table and the hash table capacity. We said that initially, if you have n items and you would like to build a hash table, you choose something slightly larger than this. Okay, so let's assume you choose something with 2n. Okay, now the hash table size is 2n, and you just move those elements to your hash table. Okay, there are 2n elements, and n of them, n of the cells are occupied for sure. So that makes your load factor is equal to what? Is equal to 1 over 2, n over 2n. When this load factor approaches to 1, that means many of the cells are being occupied and you have very few vacant cells. And this is not good for my search, because whenever I search with the hash function, I land on a position and then I keep searching, I keep accessing the items until I hit a vacant position. If I have very few vacant positions, then that means I will be spending a lot of time in the clusters. In the worst case, what can happen? If you decide to make the hash table equal to the size of your input table, okay, then everything is occupied, all the cells are filled. If this is the case, then whenever you hit to a position in a search process, whenever you check a cell, if it doesn't contain the value you are searching for, you will need to check everything. Okay, so each search will turn out to be a linear operation, which is not good. Okay. This is why, actually, when your load factor exceeds a threshold that you decide initially, you make rehashing. Okay, so this is a good time to tell about it. Okay, so I have a hash table of size m, and I insert many elements. So let's assume I decide that whenever the load factor is greater than 75%, I will double the size. Okay, now I will have a 2m size new hash table. But notice that when I resize my hash table, I need to find the hash positions of all the elements on this new hash table one by one individually. Because what is the hash function? It was according to mod m, right? And now maybe you do something, and since you increase the size, okay, so now you have the accommodation for up to 2m positions, and this will move some of the elements to their correct positions. Even in the previous case, they were colliding. Okay, so in summary, when you increase your hash table size, you perform rehashing on all the elements again from the scratch. Okay. And interestingly, it is not an easy calculation to find the expected number of accesses in a successful and unsuccessful search. Okay, but Knut did this in the 60s, and this is for linear probing. Whenever you have a load factor of alpha, this is the expected on the average number of accesses for successful search, and this is the one for the unsuccessful search. Okay, that means if my hash table is 50% occupied, then on the average, a successful search needs to check 1.5 cells. An unsuccessful search will need to check 2.5 cells. When the load factor becomes greater, okay, that means it's becoming more and more dense, then the ratios become to deteriorate a little bit, okay? But even with the very high ratios, still this is something reasonable, but the unsuccessful search becomes larger. And that is why, because you know, when that becomes dense, that means there will be clusters, okay? What is a cluster? Cluster is a contiguous space on the hash table that are all occupied. Because whenever you hit any one of those positions for a search operation, you cannot stop, right? You need to check the next position and then the next position and then the next position until you hit the empty position. That is why this is a better hash table when compared to this one, right? Because I have the length of the clusters are less, but here I have a huge cluster. So that is a bad hash table, and this is a good hash table. And then the next question is, okay, I would like to have a good hash table. How can I do it? Actually, if you would like to have a good hash table, instead of linear probing, you can try other collision handling mechanisms. Mostly, this double hashing scheme helps more than the quadratic probing or the others, okay? You can just try the quadratic probing and double hashing on the previous example with some sample values, okay? And this will make you understand those things better, okay? But that is something we should take care for the good hash tables. Okay. The last thing that I would like to discuss with you on this topic is the comparison against the balanced search trees and sorted arrays. Actually, we did this comparison at the very beginning of our lecture today. So, why I'm using hash? Because I would like to reach an constant time search performance on the average, okay? So O1, so this is an average complexity when I use hashing, okay? But I know if I did not maintain my hash table properly, that can go worse to ON in the worst case, right? So this is for the hash schemes. What if I use sorting or binary search trees, okay? Binary search trees. In these cases, my worst case and best case performances are always log n, right? So this is both the worst and best case performance. Yes, log n is worse than O1, but it is better than ON, right? So that makes hashing something in between, okay? So the problem So let me make it more concrete. Okay. So let's assume I'm using sorting. Okay. So you give me the array, I sorted them, and now I have this input. Whenever I would like to have some insertions, it will be difficult, right? Because this is an array. If I would like to insert something in between, I need to make a resize, right? So for the search, it's always logarithmic time with the binary search procedure, okay? And deletions, yes, I can go and delete something immediately, okay? From this given input, I can create a balanced binary search tree. Okay, so once I have this balanced binary search tree, my search time is again log n, right? And insertions and deletions, so they are better handled than this array insertions, that is for sure, okay? But with the hash, if I use a good hashing scheme, then the search complexity is O1, constant. That is better than sorting the array. That is better than the binary search trees, right? But the point is, this constant time search is an average time complexity. With the binary search tree and the sorted arrays, these are guaranteed worst cases, okay? That is the disadvantage of hashing maybe, but with proper usage, that might be avoided to some point. And to have this constant time search capability, what you can do is you can use larger hash tables. And that makes it a time memory trade-off. If I use a hash table with a load factor of 0.3, okay, so that means I have 3 objects, but I am allocating 10 object space for them, okay? I'm using more space. But in that case, collisions are very well handled, and you reach this average case nearly all the time. So when it becomes 0.5, it is again good. But when in practice, when it exceeds 0.5, so you need to do rehashing, okay? But there is always trade-off in computer science. So you gain some and you lose some. And the hashing schemes is no different than that. Okay, so there are some advantages and disadvantages, but it is a widely used scheme in practice. For what purpose? To have O1 search performance, okay? Constant time search performance arrives, can be achieved only with the hashing. So that is why we use them too much. Okay, so in the classroom, we will have some examples and we will study more hands-on examples, and I will try to show you why those hashing makes a lot of sense. Actually, it has been a very long lecture, so I don't want to do it now, but I will keep it included in the slides. We will discuss this later. So this is an example problem such that if you apply the naive solution, so you will have an n cube complexity. If you apply a sorting-based solution, you will have n log n complexity. With the hash-based solution, you can reach the O(n) complexity. And this is a classic improvement when we apply hashing, and this is why it is very widely used. Okay, so I know it has been a very long lecture, and see you on the next one. Okay, take care. Bye-bye.